Hello everyone, welcome for to the last week in machine learning course. And in this lecture, we will talk about reinforcement learning. As I said in the beginning, reinforcement learning is quite different than the previous what we have already seen in machine learning algorithms. So we have studied so far the supervised learning. We saw different algorithms based on the based on the supervised learning and based also on different concepts like black box or the statistical based inference or classification, and also based on linear algebra or based on the dealing directly with data like in support vector machines. So we have seen different algorithms with different concepts of machine learning, supervised machine learning. And also we studied before the concept of clustering, which is the representation of the unsupervised learning, where we have data and then we cluster them, and we study also two or three different algorithms for clustering. We also presented semi-supervised learning, where part of your data is labeled and the others are not, or also when you have to build the parameters not for the labels of the data, but for the statistical properties of each data class. So we have studied all these types of machine learning algorithms. In today, reinforcement learning, the concept is different. So, what if you have interaction with environment and you may not have any data before about what you are going to learn? So this is the one of major difference between the previous machine learning algorithms, where the fuel of those algorithms rely on data. So if you don't have data, you cannot make any kind of learning for the previous algorithms. So if you don't have any data, you cannot make learning. If you have few or small size of data, so the learning process can be biased, can be like underfitting, and also if the data is not high quality, also this will affect the performance of your algorithm. In this reinforcement learning, we don't it's not necessary to rely on any previous data or recorded data in the system, because the application or the concept of this reinforcement learning is different. The reinforcement learning is not based on supervised teaching. Means that we give the input and then we try to explain, is this picture is for example for apple, or for orange, or for like dog or cat, or no. Here we have different kind of applications where we need the intelligent agent to interact with certain environment. This environment can be physical environment or like cyber or non-physical environment, doesn't matter, but it needs to deal with environment without previous data. Of course, we have also some other kinds of machine learning or reinforcement learning, where it can also, if you have data, it will help, of course, in the speed up of the learning. But now, if you assume that you don't have any data, but we know we want this reinforcement learning to adapt and to learn by itself. Okay, how it can adapt or learn by itself? It will be based on feedback, and this feedback is not showing the right answer, but it shows if the step or the action taken by the intelligent agent was correct or incorrect. It means that when the intelligent agent takes a step or takes action, then it can receive like reward. If it receives reward, it means that it has been done in the right way. If it doesn't receive reward or it does receive some punishment, then it knows that the step might not be correct or might not at least didn't achieve the target required. Because many times in this intelligent agent, the reward cannot be immediate. Just think about intelligent agent playing a chess game. Okay, so in this case, you cannot have a reward for each step when the reinforcement learning start to play the game. Okay, so they can start with certain like movement or action, but you can it will not receive any reward or any punishment because just of the one step like or one action. The reward will be at the end when it win the game. Okay, this is one example about the delayed rewarding or delayed punishment, because if it lost the game, then it will receive punishment for that strategies or policy the reinforcement learning was playing in that game. So this is generally the concept of reinforcement learning. I'm not going as usual that to go through the slides one by one. However, that these slides have been updated, and the last version has been uploaded just a few minutes ago. So you can go there. So there are not that big change, but there are some changes in the slides by adding more examples about reinforcement learning. So we have many different application for the reinforcement learning, especially when you have dynamic environment. When you have environment which has high degree of uncertainty, and also it is time varying. So in this case, it is very hard to collect enough data to include every single case in the real environment. But by using this reinforcement learning, it can learn by itself, it can adapt to the environment, to the even it can react or respond to new cases that it didn't see, or it was not even part of from its previous experience. So reinforcement learning is very strong, actually, part of machine learning. And it is also part of from generative AI algorithms. Um, okay, so this what you can see here in the on the slide, that the concept of reinforcement learning, that we have the intelligent agent, and the intelligent agent should have like some impression at least, or some model for the environment. So it should have some model about the environment where the agent, the intelligent agent, react with that environment. The information about the environment can be complete or it can be incomplete. Okay, so it might know the environment very well, like for example in chess game. So we have very well defined environment. We have 64 squares. The agent knows where is the each item of this chess game and its location at certain time t. But if the intelligent agent is part of the autonomous car, so in the street, of course, the agent can rely on, for example, camera, implemented camera in car, maybe sonar, radar, many different like sensors in car, but still there might be some hidden things that the car or the agent cannot see, or maybe there can be some like unexpected action or unexpected event in the road. In the chess game, every action can be expected. Okay, so for example, if the players, the intelligent agent, play against opponent, and that opponent playing according to the rules of the game, so the intelligent agent might expect every or any movement of the items of the opponent for in the next state. So the state or the environment is well defined, and also it can build how will be the transition. Yes, the intelligent agent doesn't know the opponent exactly what he or she will play for the next stage or for the next step, but at least it can have some probabilistic like inference about what is expected to play next. So in that case, we say that this environment is observable environment. But we have other cases where the intelligent agent cannot see the environment completely, or the information coming from the environment is like not like noisy or distorted. So in this case, the intelligent agent might have like a stochastic, or they can rely on some maximum likelihood estimation of the state of the environment. And we can use here the Markovian process in the case that the environment is observable. So you can use the Markovian process to model the environment, like the states, the game. For example, if the game is based on, let's say, throwing a die. So in this case, you have from 1 to 6, and based on the number of dice, then the opponent will play certain action, and then the agent can represent this environment with a clear Markovian process. And in this case, it will be observable Markovian, because we know the states very well. We know the probability of the transition from each state to the next state. For example, if the agent take action to be in state 5, and then the agent waiting the opponent to play, but the agent knows also that the opponent might go from stage 5 or state 5 to state 6 or to state 7 with certain probabilities. And even in the beginning, the agent might not know these probabilities, but after playing many times with the opponent, they can also like build some knowledge about the environment by playing this game many times, and until the AI win the game, then the AI will receive a reward. But if loss, then it will receive punishment. And then we have some kind of adaptation that we will see later, how to adapt this Markovian process, or how to adapt the policy and the action from each state in order to maximize our chance to win. So this is I'm trying to summarize and to briefly explain the reinforcement learning. As I said, as you can see here, that the environment, the reward or the feedback, reward or punishment or penalty, in many cases it takes time. It takes time before it comes to the agent. Then, however, the agent needs to have some um, motivation to take or to have certain action. Because of that, even if the reward is delayed, we can build the algorithm in order to estimate this like a cumulative reward, as we will see soon. Okay. So this is the reinforcement learning briefly. So as you can see in reinforcement learning, coding, when you code the reinforcement learning is different from the coding in machine learning. Because in machine learning, we rely on a predefined data set for training. However, the reinforcement learning relies on an environment function. So when you write the code, you will have environment function that simulates the interaction between the intelligent agent and the environment. So the reinforcement learning agent takes an action based on its current state and the learned policy, as we will see soon. So the environment function then return, remember that in this function, when you write the code in this function, so you will give to that function which is representing the environment, the state, the current state, and also the action. In each state, we may have different kind of actions depending on the current state that you are in, as we will see also in some examples. This is your input to the environment. And what is the return from the environment? The return from the environment is the new state. By the way, when you play with this reinforcement learning, the opponent can be natural, can be the environment itself, or the opponent can be another opponent, or another intelligent agent, or the opponent can be another person. Okay, so you play with different kind of cases or situations here. So now the environment will return to you the new state resulting from your action. So you take action, so then you will receive the new state. You may ask me question. Since you know your current state and you take specific action, you should know exactly what will be the next state. This is true in case of deterministic games. Deterministic, fully observable, non-dynamic games, static games. However, in reality, you may take action and receive different thing, different state. For example, if you have a robot and this robot, it has some like malfunction or fault in motors. So in the arm of the motor, okay, you as intelligent agent give the motor that to move, for example, with certain angle to the right. So because of the fault in the motor, that it will goes further angle your action. So your action like go by over 3 because of the malfunction, because of the fault in the machine. So it went like by over 2. Okay, so now the new state is different than what you commanded the action. So you are not working with the environment blindly. You need all the time to have the feedback. So in the feedback, you will know that this is another state different than the state that you have designed to have or to go to. Then also, the function should return to you a reward or punishment, indicating the action desirability. It means that it is desirable action or not. Okay, so sometimes it returns nothing, it returns 0. So no punishment, no reward. So just delayed. Okay, and 3, a termination signal. For example, if you reach, either you lose or you win the game, or you end to some state that it is end state. The end state is the state where it returns to itself with probability 1. So if you reach to that state, either you lose or you win, but that state means that you cannot move from out from that state anymore. So you need also to have this. So optionally, you can also have different kind of information related to the learning, because we have also what is known as like deep reinforcement learning, where we have a neural network in order to model the environment. So some environments, they are very complicated and cannot be modeled with simple Markovian process with finite number of states. If we want to do it in states, we might need like millions or thousands of states, which makes the learning almost impossible. So in this case, we can use like deep learning in order, or a neural network in order to learn the environment. So we learn the environment not in simple Markovian process, but with more complicated and more efficient way by using a neural network or deep learning algorithms. Okay. Here, as it was explained in the recorded lecture, we have a single state case. Why it is single state? Because in this state, we don't have like, we are not going to different states. We have the single state, but we have many actions in the same state, like this one. So you can see, so we have a single state here. We are not moving from state to state. We have single state, but we have different actions. In this different action, we have k different action that we can deal with this game. So it is like hidden game. So you don't know that by pushing any of these k buttons, you might get some result. It is like you have k doors in the front of you, and behind each door, you have something hidden behind each door. Now you want your reinforcement learning, or you want to build intelligent agent in order to select, to explore first and then maximize its reward. In this very simple, and maybe this is the simplest reinforcement learning we can model, that we have a static case and we have like instantaneous reward or punishment. So the feedback is instantaneous that you get it. But we don't have learner here. We don't have teacher. We don't have anyone to say, to tell you, go and select number one because there is 1 million euro behind it or behind that door. No one explained this to your intelligent agent. So you need to check. Okay. Assume in the beginning that you don't, this intelligent agent doesn't know anything, what is like unseen behind these doors or behind these buttons or these doors. So in the beginning, the intelligent agent will start what is known as exploring the environment. Okay, because as I said, in many cases you don't have any previous data. The intelligent agent wants to explore the environment. So this process is called exploring the environment. Exploring the environment makes this intelligent agent to select any number from 1 to k. And this could be selected randomly because you don't know anything. Just imagine about you yourself. You are in front of 5 doors and they told you there is a big prize behind one of these doors and you have no information at all. So in this case, you just assume that you select each door with a probability 1 divided by k. If k is $5, then it will be 20% to select any of those doors because you don't have any information. So the intelligent agent let us assume that it has select number 2. So when it selected door number 2, it receives 2 euros. Okay, so this will be the feedback. The feedback is rewarding, not that big reward, but we don't know. Maybe in the other doors, maybe we have big punishment or big penalty. So 2 euro at least is greater than 0. So the reinforcement learning agent will be happy. Okay. In this case, the reinforcement learning has 2 options to play: either to exploit or to explore again. What is the meaning of exploitation? Exploiting means that since they got 2 euro, and it means that because the game is repeated. So every time you open the door, you will find 2 euros. You take them. Every time you open the door, you find 2 euros. You take them. So this means that exploitation, because the game is static. A static game means that it will not change this feedback. It is not time varying. So if you are satisfied with 2 euro, of course you can continue forever with 2 euro. But in machine learning and in reinforcement learning, we it is good always to exploit. The exploitation means that you give certain probability that instead of exploit the same good 2 euro, you check with another doors or buttons. Okay. Now assume that the reinforcement learning decide to take number 3. So when it takes number 3, it comes danger, crocodile here that we can see, which has eat all the money that the reinforcement learning has collected in the previous, like by exploiting number 2. So now the reinforcement learning will mark number 3 as dangerous. So it will not try to do it again because it got big penalty. And this game is, again, the game is deterministic now and static, which means that every time behind the third door, you will have this penalty. So you will not try to do it again. So you put this as big dangers, maybe minus 1,000. So I will not come to this door anymore. But now you need to select again. So you can go back to number 2 where you get 2 euro, but you can also try another door. So assume now they went to number 1. So they get 1 million euro. Okay, of course, since it got that much money, maybe it is good to exploit it more and more and more. And in this case, the probability of exploiting will be much higher than the probability of exploring. Okay, so maybe the reinforcement learning, it will decide to exploit this number 1 with a probability 0.999. So it generates like some random number epsilon from 0 to 1. And if epsilon is less than 0.999, it means that it will exploit. But if it is more than 0.999, which means that the probability is very, very small, then it will go to exploration again. So if it go to explore again, but of course it will not go to number 2 or number 3, because it knows now in number 2 there is 2 euro only, in number 3 it is dangerous, but it can also explore with the other doors. So this is the simplest reinforcement learning algorithm that you can see. So it is a single state with many actions. We have k armed bandit here, so we have k actions, k possible actions that you can do, but in a single state of the game. Okay, the problem can be slightly more complicated. What if what is behind the doors is not fixed, but it can change with certain probability? So maybe in the first door, there's 1 million euro, but it has chance also to be only 2 euro. Or the dangers can be also in the first door. So now in this case, what the reinforcement learning agent or the intelligent agent, what it needs to do now? Actually, what it needs to do is also to learn, okay, these probabilities, these transition probabilities between the rewards, or between what is behind that door. But still, we have single state. Even here we have multiple states, but the multiple states is based on what they can get. It is now, instead of saying that by opening the first door, you will get 1 million euro with probability 1. Now we don't say that. We will say that after opening the first door, you will get 1 million euro with a probability, let's say 0.1, but you will get also €2 with a probability 0.3. You will get some dangerous action with probability 0.05. You will get this and this and that. And then in each door, it will have certain probability about what you will get or what the reward that you want to get you will receive. Okay. In this case, how could we play the policy? We will use the same concept of exploring and exploitation. The only difference here is that instead of being sure about the reward, I will use the expectation of the reward. The expectation of the reward, not the reward itself, because the reward itself is unknown. The reward now is changing, or the punishment is changing. But for each action, we will have some expected reward that it can be positive or it can be negative. If it is negative, of course, it will be penalty or punishment in this case. Okay, so now instead of using like deterministic case, we go to the stochastic or including the uncertainty in the reinforcement learning. Okay, so this was explained, and you can see here in this slide that instead of using the R is the reward, now instead of R, I have the distribution, the probability distribution of the reward given action A. So based on the action A, then you have distribution of the reward. Of course, if the reward is discrete, then you have a probability of the reward. Okay, so in this case, maybe I can I will try to write something. So now, instead of having the reward for each action, because usually we represent the reward is based on action A. A belongs to, for example, all actions that you can take in that. Maybe you have N action, or actually we have K action, because we have single state. We have single state here, and in this single state, you can take different actions, A1, A2, up to AK, represented by those buttons or the doors. Okay, so now A belongs to this, and we saw that behind each action we have certain reward, so we represent them as R of A. So this is the reward based on the action. For example, R, maybe the action is 1, so it is 1 million. Action, the reward of action 2, it was €2, and so on. Okay, now because it is becomes, we have uncertainty, we have stochastic reward. So in this case, we have the distribution of the reward based on the action. So we have distribution now. And this distribution, in case that the reward is continuous, like in signals, for example, like in the share price for certain company, and based on the action taken by that company, then the prices or the distribution of prices can be fluctuating between some values, for example. But if the rewards are discrete, for example, you have like R1 equal to 1 million and R2 equal to €2, and so it is discrete. So in this case, we can represent this as the probability mass function. So the probability of R, given that A equal to, for example, certain AI, for example, if based on the action. So this is the action. If you take this action, what is the probability that you get certain R? For example, R equal to R1. What is the probability that you get R equal to $1 million, given that you take action equal to the first door? This will be now probability. Okay, so now we start to look to the problem and by this angle. I know that some of students, they don't like to include, and every time that we bring this like conditional probability and Bayesian function in everything. And this is unfortunately, maybe unfortunately for those who don't like this approach, this is the okay, some people maybe they don't like when I say that is the only way, but in my opinion, this is the only way to deal with uncertainties. Okay, so some people they like also they say that okay we have also linear algebra, we can do nice things with those. Yes, sure that linear algebra is also a strong tool, but in order to have like full awareness about the problem, this is the only way that we deal with uncertainty. And when the reinforcement learning actually or the intelligent agent, it should work in real problems, and in real problems usually it is full of uncertainties when it deals with physical life, like robot or robot moving in some way, or we try to understand some behavior of people or something. So we have a lot of uncertainties that we need to take into account. Okay, of course, if you deal with very well, defined problem, like solving some differential equation, for example, there are some steps. Maybe you don't need to go through these techniques, these technologies, because we have very systematic way to solve these problems. But in real problems, in real life, we have a lot of uncertainties that we need to take into account. Okay, okay. Let's go back to the slide. Sorry, this is the problem that when you have many screens open, so you need to bring everything to the same screen in order to be able to share the slide. Yes. Okay. So now you can we come back to the slides. Um, how to find the optimum policy in this case, and how to formulate the optimization. Now we want to optimize the reinforcement learning. We wish this reinforcement learning will take the right actions toward that it will win at the end. So this is our objective. Our objective that we want this intelligent agent to take by itself without our interfering to it, without giving any supervised learning. I want this machine to be able to select the proper action in every state in order to win at the end of the game. And when I say game here, I don't mean the game for fun. It can be this reinforcement learning. It can be a robot that fight in war field. So it is also game. It can be actions taken in order to maximize the profit in certain company. So how to play game against another companies, like in game theory, for example. But now they have actions here for the reinforcement learning that it should be taken by itself. It can take actions because the environment is a statistical environment, and in each state they have finite number of actions that they can take, which one that it should lead at the end to win the game and to have like higher or to maximize the reward or maximize the profit of a company and so on. So the game is it has very wide meaning. It is not necessarily only the computer games. However, of course, it is applied also in computer games. Um, now, if we define, because we have a single state, if we define that the reward by Q of A star, and then you select A star in order to maximize the reward. So it is the maximization of the reward of the game. This is in case of single state. And we can go in this way, of course, because as I said, that when you take the action, is not always that you get the same reward. So even if you take the same action, you select the button one, you get €2. You select the button one again, you get dangerous, eat the €2. Put it again, you get €1,000. You put again. So even if you repeat the same button every time, you will get some different reward. Okay, what is the important thing for you in this case? What is the indicator for you? Remember that the reinforcement learning is a process that it repeats itself for hundreds and thousands of times. Okay? So in this case, during the learning, I mean, okay? So in this case, what is the number which is very important for you? If the instantaneous reward is changing every time, so of course, the best thing to do, or at least one of the best action or the best parameters that we are looking for, is to look to the average. Now I start to look to the average. What is the average of getting certain reward by playing certain action? Okay, so if the action is selecting the first door, on the average, what is the reward of this door? If the action is taking that you open the second door, what is the average that you will get after the second door? If you have been informed that by opening the first door, the average, you will get Ferrari car. This is the average of the first door. It doesn't mean that you will find Ferrari car. So you might get bicycle, you might get airplane, you might get, but the average is Ferrari car. The second door, the average that you will get single euro. Of course, everyone will go to the average, the higher average, because the higher average, it means that your chance to win, your chance to get higher profit is by going to the first door. Even the second door, the average is €1. Maybe there is a probability 10 of minus 10 that you will get $1 billion in the second door. But this probability is 10 of the minus 10 or minus 8. But the average is $1. So of course you will go to the first door. So the average is one indicator for us that we need to select based on the average. Clear? Okay, fine. But who will give me the average? Who will inform me the average? No one. Because as I said, we don't have here like supervised learning. You need to learn this by yourself, by going from exploitation to exploration. So by moving to explore the environment and explore, by doing this many times, at the end, you will converge to the average behind each action that you are doing. Is it clear? So it is very important in reinforcement learning. In reinforcement learning, we try, now still I'm talking about single state. I will extend this now to the multiple state scenario. Okay, how to do this? We can do this online by updating by this function. So what is the QT of A in front of you? This means the average reward by taking action A. I repeat, QT of A is the average reward at time t by taking action A. Okay, what is RT plus 1 of A? RT plus 1 of A is the actual reward you get by taking action A. It means that you take action A, what you actually received is called, you put it here as RT plus 1 of taking action A. Okay, what is delta here or eta? Eta here is called the adaptation or the learning parameter, which is usually less than 1. Okay, now when you compute all this, you put it, the result, you put it at qt plus 1 at a. What is the meaning of a qt plus 1 at a? It means that this is the average reward, okay, obtained at time t plus 1 by taking action A. Now you are building your knowledge, your intelligent agent, your reinforcement learning. Try now to build this Q function. And this is the name, actually, we had name it like Q learning, which is the major learning algorithm in reinforcement learning. Of course, there are maybe more than 10 or 20 different algorithms there in literature, but the basic or the basis of the learning is based on the Q learning. So the Q learning in single case, in single state, in its simplest form, is following this one. So you try to build the Q, the average reward that you obtain from taking action. After repeating this many times, you end up by a Q. It will converge. This Q will converge to some value. Then you will have the reward by taking action 1, the reward by taking action 2, the reward by taking action 3. Of course, you will select the maximum. Of course, you will select the maximum average reward that you obtain. There are some special cases. They don't use the average. They use the median, which is nonlinear of estimation, or they use mode or whatever. But here in this lecture, we continue with the average reward. Okay. So this is called delta rule, as I said, and actually I just wrote here very simple code in order to show you how this delta rule could give you the average of the movements. So here I generate this blue random signal. It is random signal, but changing not very fast. And then the red one is the delta, and you can see that the delta all the time can give you some averaging of the changes of this real signal. So it is called delta rule. It is well known, and I'm sure that many of you have already seen this in yes. Many of you have seen such kind of algorithms in different signal processing courses. Okay. Now, the question is, what if we have different states, not a single state? We have now different states. Okay. When you have different states, then at each state, you will need to compute what is the probability to get the average, or so the probability to get certain reward based that, or given that you are at state I and you take, or the intelligent agent take action J. So this represented by the Q, so it is more like a generalization of the single state case. So now we are talking about multiple states. So when you take action, actually now, what will happen? Previously, in the simple case, that in the single state case, when you take action, you get some reward. And this reward, as I said, it can be stochastic reward. Then I need to average this reward by repeating this action many times. Now, in multiple or in multi-state environment, when you take any action, if you are, for example, in state I and you take action, certain action, this certain action will have two impacts, not one impact. It will have one impact about the reward that you will get, and also it will have another impact on the next state that you will move to. So it is not as in the previous trivial case when we have a single state. Now we have multiple state. So by taking the action, it means that you move from state to state, and then it will affect your your reward as well. And this representing by Q of SI and AI or AJ. So actually, this could be represented as a matrix. It is called the Q matrix. A Q matrix. SI is the all states that you will get from inside the game, and AI or AJ are all actions that you can do in each state. And based on this, what is a Q? A Q here is the average reward that you will get by selecting or by being in state I and you take action AJ. Okay, so let me, yes. So this process, when you have multiple states, we model the problem by using what is known as Markov decision process. It is very similar, by the way, as the Markovian process that we saw in the previous week and also the hidden Markov model that we saw before. So they are very, very similar. The only difference here is there. Here, in each state, we define also the possible actions that you can do. So not every state that you have the same set of actions. Okay, let me give you example. I don't want to spend too long time here because those things are already recorded. But let me give example. Stop. Okay. Now assume that you are in maze. Okay. So in this maze that we have a room here and we have a room here, and then we have maybe another room here, and we have the yeah, okay, it can be something like that. Okay, now in this maze, I can define that the game has states. So the state here is the location, because I can divide this into rooms. And now the rooms of each room here, maybe this is 1, 2, 3, 4, 5. Okay, so now you have a robot, and this robot can move in like 4 directions. So your action is up, for example, and right and left and down. I gave some example, and also I wrote the code you can find in the recorded lecture to solve similar problems like this one. Okay, so now the reward is for the maze or for the robot, which is somewhere here, for example, is to get out from this maze. So once it gets out, it will get reward. Okay, otherwise it will not get anything. Or maybe for each step it can be negative, in order to make it, that this robot is or this reinforcement learning algorithm should work against time. So in order to work against time, you can have for each movement, if it is not to be free, then it will receive -1. And the Q learning algorithm, we try all the time to maximize the reward. So this negative, it means that it will reduce it. Okay, so if we are working with observable states, it means that the machine learning now, or the reinforcement learning, or the intelligent agent now knows the state where it is now. So now it is in state 3, as you can see. Okay, in stage 3, you can maybe just let me remove this to this way. Yes, let me just change this little bit so to have Okay, so this is number 5, and this is to get plus 100 here. Okay, so now in this is state 3. From state 3 you can go to state 4. Okay, and from state 4 you cannot go anywhere, you can just go back to state 3. From state 3 you can go to state 2. From state 2 you can go also to state 3, and from state 3 you can go to state 1 and also back. And from state 5 you can go back, you can go from state 3 to state 5, and you can go back, but also from state 5 it can go to the when case. And in when case we have it is absorbing state, which means that once you reach to this win, then that's it, the game is ended, the game is over. Okay, so now if you deal with observable Markovian, it means that your machine learning or your intelligent agent knows exactly in which state it is now. So now this movement actually is not based on a probabilistic. It is not probabilistic. In the simplest case, now we deal with deterministic situation, that I am sure that my robot, if I give it with like to go to the right, it is now in 3. If I go ask to go to the right, for sure it will go to state 2. And if I give from state 2 to the left, for sure it will return back to state 3. And from state 3 to the right, to the left, it will go to state 4, and to the right, it will go back to state 2. Okay, and from state 3 to up, it will go to state 5. This is up, and down, it goes to state 3. Okay, so you can see, for example, in state 4, if you are in state 4, the action space that you have is only one action that it is allowed for you. The only action is allowed is to go to the right. If you are in state 4, you cannot go to any other state except state 3. So the only action available for you is right. You don't have other action. But in state 3, you have all 4 actions possible. If you are in state 3, you can go up, you can go right, you can go left, you can go down. But if you are in state 2, you have only one action defined, that to go, for example, to the left. If you are in state 5, you have 2 actions, either to go down or to go to the right. If you go to the right, then you will go to the win. Okay, but now for the reinforcement learning, actually it doesn't know any or the configuration of this maze. Your robot doesn't know the configuration of this maze. What it knows its current state. It knows only its current state. When it moves to 4, it will know that now it is in 4. Maybe there is some like camera in the robot. We have camera here, and maybe there is number that it can read. So it can read that now it is number, it is in 4. So it is observable environment. The environment that in this simple example, the environment is observable. So it knows where it is, but it doesn't know anything about the configuration of this maze. How it will work? How it will work? How this reinforcement learning algorithm, how this Q algorithm will work? It is in the same way that we saw just now when we talk about single state. But now the difference is that we know in the beginning, the Q matrix, which means that the Q, where you have the states that you have, maybe state 1, and the actions that you can take. Okay, so for each state you can have matrix, and in this matrix the rows of this matrix are the states. Here I have 4 states, 1, 2, 3, 4. Okay, and then I have the actions, possible actions. So the possible actions are, for example, left, okay, right, down, up. Those are the all available actions that you have in this matrix. This is called Q matrix. This is called what? Q matrix. In the beginning, this RL, we don't have any data. You take this reinforcement learning machine or driving machine, you put it in this maze. So in the beginning, the brain of this intelligent agent, all zeros. It is like baby, like newborn baby. Know nothing about the environment. All zeros. Okay. Now they start of what? They have nothing to do. Only thing that they need to do is exploration. So they now to start to exploration. What is the exploration? Exploration that it will need to know first, where am I now? Okay. So because now they don't know anything in the beginning, except maybe, as I said, you have a camera that you can read that your current state. So of course you can start from any state, not necessarily from three. Maybe you put it in number one. Okay. So now in number one, the reinforcement learning doesn't know that number one doesn't have any opening door except to go up. Doesn't know that in the beginning. Even the reinforcement learning doesn't know what is the meaning of up and right and left and down. They don't know what is the meaning. But what it knows that it has to take only four signals. Take four signals. Either, for example, let's say 1 volt, 2 volt, 3 volt, 4 volt. For example, if it takes 1 volt, we convert it to some digital number, which means, for example, up. 2 volt means down, 3 volt means right, 4 volt means left. So now in your code, you define these four elements that they need to go. So in the beginning, it doesn't know, as I said, what is the meaning of these signals, what is the meaning of this room, no nothing. So it will start, let's say, by going down randomly. It will select any random number, 1 or 2 or 3 or 4. It will take, for example, in the beginning, number 2. Number 2, it was here, it goes down. When it goes down, it will hit in the wall. Okay, it will hit. It start the engine moving, but it doesn't move anywhere. After let's say 1 minute or 30 seconds or 20 seconds, the reward will come. So the reward will come negative, -1. The -1, this machine now, this Q matrix needs to adapt this minus inside our Q learning algorithm, as we will see in terms of equations. It means now this action is not good. As I said in the beginning, when in the single state case, that when it gives that when you open the door and you get negative, it is because always we are looking to greater than 0, and we are always looking for maximum reward, maximum average reward. Now this is negative. Of course, it will not think to exploit to go down anymore. So if you are in room 1 or in state 1, you will not go down, because down will take you to no way. You will get always -1, -1. If you repeat it, of course, in the beginning, because they try to adapt it is experience, they try every time different direction. So if it is repeated again, down, every time down, down, always -1, -1, -1, then it becomes like the average -1. I will not go to down anymore. Okay, now it can go up. It goes up, it becomes in 3. When it comes in 3, what is the reward after 30 seconds? -1, because it didn't get out. Then explore again. Go left, go down, go up, go left, go down, go right, go left. Thousands of times of trying. Of course, not necessarily thousands. And this is a very simple game or very simple case. So it can take just a few tens of times before it built the brain. The brain of this machine learning, or for this reinforcement learning, is this matrix. After repeating many times, you will get the average reward by taking, if you are in each state, you will find the numbers what you should do. For example, if you are in stage 3, you will find here, for example, point 1. You find for right, maybe also point 1. You will find to be up. For example, to go down, maybe it is 0.01, and to go up is point, for example, 75. Okay, so the maximum is to go up. So wherever you are in stage 3, the maximum Q, the average, this is the same average that we saw before. The average, if to go to up, then automatically it will take to go up. Okay, and by repeating this, as I said, 10 times, then independently, without our interfering with them, we didn't give it any like teaching or instruction, by itself, by this critic in the feedback, this is wrong, this is right, -1, -1, -1, then suddenly get 100. Okay, so 100 is big reward. So it learned by itself that this is the target that it needs to go. You can repeat again and repeat again and repeat again until you get this matrix will converge to some numbers, and those converging or those final numbers, it indicates the strategy that the machine learning or the artificial intelligence will need to follow in order to get out from this maze. Okay, there's one thing interesting here. After this learning of this, and you get such kind of a Q matrix or adapted brain for this reinforcement learning or for this intelligent agent. Now the intelligent agent start to have some experience how to deal with such kind of games. If you bring another maze with different opening door or with different structure, they found that the intelligent agent which had seen some different even maze, they start to adapt or to learn faster instead of starting from all zeros. Okay, so now we have more and more experienced intelligent agent. So this is the main concept of the reinforcement learning and how it works. Okay, but what if you don't know, even you don't know the number of rooms? Or what if, let me go to the other one. Now we say that you have S. Those are the three doors that we have. 1, 2, 3, 4. Sorry, 4 rooms that we have. Maybe we have also 5 rooms in the previous example. I said that if you are in room 1, there is no connection to room 2, as you can see. From room 1, there's no direct connection to room 2, but from room 1, you can go only to room 3, as I said. So from room 1, you can go directly by going up to room 3. Okay. However, if we want also to include some uncertainty in the movement of the robot, as I said before. So assume that what if when you set the signal up to the your robot, when you give the signal up, it didn't go straight. So the wheels were a little bit tilt. So instead of going to room number 3, it goes to room number 4. And it is possible this to happen. Assume that it is possible that to happen such kind that you don't have control over the wheels of this robot. You don't have full control. You might have some control, but you cannot guarantee 100% that when you make up, it will go to number 3. So in this case, we have a probability. So we have probability that when you say up, the probability, let me now remove this one. So it can go with command with A, what is the equal to up? This is the action up. So there's a probability to go to state 3 or room 3. So this is the probability that you have state 1, okay, in state 1. So you have state 3, you was in state 1, and you take the action A equal to up. This probability, instead, in case that we have deterministic situation, should be 1. But now you can put it like 0.9. And then we have another chance that we will go, the probability that you will go to state 4, given that you was in state 1, and you take the action equal to up, it will be 0.1. Of course, remember that always the summation, the summation of all states coming from certain state should be 1. So this is 0.9, and this will be 0.1. Now we have included the uncertainty in our problem, which is more realistic. More realistic. Always, as I said, always when we deal with the real problems, we have to include the uncertainty. There is nothing guaranteed 100%. Okay. And the same thing, it can be done for the all the other movements. So for each movement, you can include the probability from to being in S4, given that you was in S2, and you take this certain action equal to blah, 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 and this can, for example, 0.6, and now we can include the probability. You might ask me question, why I need to compute the probability? This is a good question, because we need to compute the probability in order to compute the average reward, because the average now, the reward is not guaranteed. That because if it is only 1 and 0, the probability that we can easily compute the average reward in somehow in deterministic way. But now we have in a probabilistic way. So we can compute the average of getting certain reward, because we need to multiply each one in it is a probability of happening, as we saw in the probability part in part 3 in this course. Okay, so taking these probabilities of movement. But if I ask you a question, is this in front of us now that we can see in front of us, is it observable or hidden, Markov? Of course, it is observable. It is still observable. Yes, I don't know when I give up action. I am not 100% sure if I will go to room 3 or I will go to room 4. I don't know exactly, but once I move it to that room, I will know. Remember, this is very important to remember that in the beginning, you are in room 1, you take the command action of up, go up, okay. But once you go up in the beginning, you don't know if you will find yourself in the second state, you will be 3 or will be 4. You don't know. But once it happened and it is moved, then with your camera, you see that you are in room 3 or you are in room number 4. So it is observable Markovian. It is still observable. It is not hidden. It is not hidden. When it will be hidden, it will be hidden if we don't know, there is no, or there's some rooms with no numbers. This can be like more tricky and more complicated situation. If some rooms, the camera, when it goes to the number of the room, it couldn't find the number. So now when you go up, you can be in 3 or 4, but you don't know, is it 3 or 4? Okay. So now we can deal with, it is called like partially observable hidden like a process. Partially observable. So some are observable, some are not observable. Of course, we have, we can also include the probabilities as we have seen in the previous hidden Markov models. Okay. Is there some other example maybe different than this robot and moving in rooms. Yes, of course. For example, if we think about this chess game, okay, so in chess game, so the current state that depends on where are your items on the field and your opponent items on the field at time t. So those are visible for you, for your intelligent agent, for your intelligent agent. So they know, or artificial intelligence. Sometimes they call it artificial intelligence, AI or IA. So in the beginning, they know the state. So the state of the game is the current state at time t. But what will be the state at time t plus 1? So maybe you consider the state of the game is not when you take your action, but when you complete the action. It means that you take your action, your movement, and your opponent also take her movement. So if you move here, you decide to move here, okay? So now you are at state I. The next state depends also on the movement of your opponent. So you can go from state I to state, for example, K1 or state K2 or state K4 and blah blah blah. So now you move from state I to which state you don't know. But for each state, you will have certain probability. You might move from state I to any of those states with certain probability because you can guess what is the probability your opponent will pay with that movement. Okay? But once you move now, you can once your opponent move their own item, then you know what is the current state in which one your opponent moves. So by playing this many times, you can also determine the probability of your opponent if you both, of course, at stage I, how your opponent think to play their own movement based on your own movement. By building these probabilities, by playing this game maybe thousands of times, this is the reason that this reinforcement learning, when they play chess in the beginning, they make the chess to play against each other, computer against computer, and very fast computer against very fast computer, in order that they learn the process how to the play. So they try all the time to play against each other until they got some general rules and also some clever way to play against each other, because every player plays with certain probability in exploitation, in exploration, and they use different strategy. So and you are as the programmer of this reinforcement learning against each other, you can put different strategies for each player, and then they can learn from each other after they playing to against each other like thousands or tens of thousands or millions of times. They become experienced enough to start playing against people. Okay, and they start also to learn and adapt the probability, and they start to catch the strategy of the human, how they play in order to beat them. Okay. um Let me go back to the slides. So as I said, this is called the states that we have seen together. It's called Markov decision process, MDP. It is very famous, very well known algorithm, not only in reinforcement learning, but it has many applications in decision making algorithms. It has application in business and in finance. So it is called Markov decision process because it is very similar, as I said, to the Markovian process and hidden Markov process. But now we have action at each state that you can take, as I explained now. Okay. This is now how to compute the reward. So the reward can be propagated or accumulated reward, because the reward, so it is the easiest thing when you get the reward immediately after taking the action. But unfortunately, this is not happening. So we need to estimate the reward. Even we didn't get any reward, we did sometimes you take action, but the environment function reply you with null, with zero, nothing, no reward, no punishment. Okay, but at the end, when you reach to the winning state, so you can distribute this winning, for example, plus 100, you can distribute them over all the states that you have done before, in order to motivate you to take the state which is the best state to take, which can lead you to the winning in minimum number of steps. For example, if you play a chess game, it is better to play to win after, like, let's say, after 10 movements, much better than to win after 1,000 movements, for example, if possible, of course. Or in the maze, it is better for complicated maze, for our robot to get out from the maze like within 20 minutes is better than it takes like 20 hours. Okay, so in this case, maybe in the beginning it will take 20 hours, because it needs to explore, making exploration every time. But once it reaches to the solution, how to go and how to distribute or how to optimize our policy back, okay, until we find the best path to get out from that maze. That what is need that we need to distribute the winning or the reward through all the steps. For example, some step, even in the actual game, in the exploration phase, you will get nothing. But after like taking this trial many times, maybe taking this action, it will be negative. You will receive some kind of negative like penalty, not from the environment. You get the penalty from the algorithm. The algorithm says, don't go in this direction, because this direction, it will take long time and finally you will come back. Okay, so this should be clear. So now, how to compute? This is v by of st. What is the meaning of v by of st? It means that if you are at state t, at time t, and you are at state t, as I said that now we talk about observable Markov. It is not hidden. If you are in hidden, you don't know in which state you are, but you can guess. But now let us take the simpler way. So now you are in a state at time t, and you are in a state st. Okay, what is the expected reward that you will take, or you will receive by the future? This is very important in dynamic programming, that usually don't look to the past. Look always to your current state. So look always to the future. For example, maybe I spend 20 hours in the maze, and my goal is to get out from this maze. I will not sit and cry because of the 20 hours, because the 20 hours already done. Of course, I will get experience from them. But now I am in state st, at time t. I am looking for the future. What is the minimum steps that in front of me to get out from this maze, regardless how I reach to this state? This is well known like policy. It is very well known in dynamic programming. Those who take maybe course in optimal control, they know this very well. Okay, look to the future. What happened has happened. Look to the future, and now what happened before, we will get experience from it. But always look to the future and how to get the maximum reward from the future, not from the past. The past has done. Okay, so now if you are at state st, at time t, what is the expected reward in front of you? The expected reward in front of you is the expectation of RT plus 1, the next step reward, the next step, the other step reward, the other step reward, until you end to the time t capital. Maybe after, maybe this called finite horizon. It means that the number of steps are known already. So in front of you, you have still, let's say, 10 steps before you reach. Okay, so in this case, we can give it in this way. Okay, what is the RT plus 1? RT plus 1 is the reward that you will get by taking the next state by taking the action AT. So because you are at state T, you take the action. Based on this action, it will move you to state ST plus 1, and in state in ST plus 1, you will get reward RT plus 1 on the average. It is the expected. It can be plus, minus, it can be increased, decreased, but this will be in this case. Now you are in T plus 1, in state ST plus 1. You take action AT plus 1. You will move to ST plus 2, and you will get reward RT plus 2, and so on. So these actions, this series of actions is called the policy of the reinforcement learning. So you can see here, the policy by is a mapping between the state to action. In each state, you can take certain action, as I show previously that you are in room number 3. You have 4 possible actions. You are in room number 2, you have 1 possible action. So the available actions for you depends on your current state. In case that you have observable Markov, or observable environment, or partially observable environment. Okay. However, if you don't know how many steps in the future in front of you, like in the maze where we don't know how many doors there or how many rooms. Maybe we have 20 rooms, or maybe you have 100 rooms, or maybe you have 1,000 rooms. I don't know. So in this case, the previous model is not working, because in this model, that if you have infinity of very large number of steps, then the expectation of infinity number of rewards can lead to infinity. So in this case, we can use what is called like discounted rate. The same equation, but we use some discounted rate. As you can see, the expected of the next reward, if you are in state ST, the most important reward that you will get is the next state. For example, the next state, the reward of the next state, it will be RT plus 1. But the reward that it is obtained at the 1 step further, it will be multiplied by discount rate is alpha, and alpha is between 0 and 1. Actually, there is some there's two benefits of using this alpha, and it becomes alpha square, alpha cube. As you can see that as you go further in the future, the value of the reward you will get in further in the like foreseen, it will have less value for your current case. So you are more interested in the nearest reward than the farthest reward. If I ask it any one of you, what you prefer, today you get in your hand 1,000 euro today, or you get 100,000 euro but after 10 years. I am almost sure that most of you will decide to take the 1,000 euro today than preferred on the 100,000 euro after 10 years. Nobody knows what will happen during these 10 years. I want to enjoy today. So this is the concept. There's a concept here that the far away reward is not that interested as the closest reward. So this is the way they bought discount rate. Then of course there are more and more explanations about the algorithms. It was already given in the in the recorded lecture. But here, for example, the optimal policy. This is important also concept that I wanted to focus here. Usually you are looking for the optimal policy. The optimal policy is the series of action that you take in order to maximize the average reward of the game once you are starting from state st. You are at time t, you are in a state st. So the optimal policy is the policy which gives you the maximum accumulated reward. The maximum accumulated. It is very simple concept. There is nothing, I mean, tricky or hidden here. It is very simple and it is very also intuitive. I am now in state st at time t. I am looking to achieve certain objective within like 100 steps, 100 days in front of me. The best policy that I will take is the policy which will maximize the average accumulated reward that I will get during the future from today. You cannot get this from the beginning because, as I told you, your RT or your RL, reinforcement learning agent, doesn't know the future. We don't have data, so they need to try. They learn trial and error. They try until they reach to the end. Once they reach to the end, they have experience, as we saw in the maze game. Once they have experience, then if they come back, they found themselves from the starting point, and they experience it during their movement. They didn't experience it every path, but they experienced some of the paths. And they knew some of the paths are bad, and they knew some of the paths are good. Then they will try to select the better path. And when they repeat again, they can exploit the good path, but also they can explore another different paths. And after training the other different paths, maybe they find better path than the previous path. So the policy is adapted. So the policy every time it can be adapted and improve it and improve it and improve it until after repeating this many times, you will get to the optimal case. You will converge to the optimal case by trial and error. And we use what is known as the optimal or the sometimes they call it like Billman's equation. Okay, in dynamic programming. Uh, Sorry, today I take much longer time than expected, but that what later you will have different codes, and actually I added also some new slides here. For example, the Q-learning algorithm in simple steps, because here we have some mathematical analysis for different kinds of situation like model free or model based, deterministic, non-deterministic, different algorithms. But what I have explained within this online session is enough to understand the concept of reinforcement learning. However, that here I added these slides based on how to summarize the Q-learning algorithm in simple steps. Okay, and after that, what is the application of Q-learning that we have seen today? It can be applied very well in case of small and discrete state spaces, in case of fully observable environment, and in case of policy learning. That means that you learn from experience, so you can repeat it many times. Okay, and when the Q-learning fails, the Q-learning fails when you have large or continuous state space. So we have what is known as curse of dimensionality, that when the dimension is very high, so you need to try this and this path, and this path means, for example, remember, just think that if you have arm, and this arm, it has 7 dimensions to move, like it can move x and y and z and with different angles. Okay, and now you want to try like thousands of cases to in different scenarios. So this can be very a huge number, and this Q matrix can be like almost infinity. It can be like hundreds of millions the dimension of the Q matrix, which makes the learning is not possible actually. Okay, so in this case, we can model the environment instead of using finite states as we saw in this Markovian process, in decision Markovian process. Now we can use like neural network or deep learning instead of the Q table. So we have the Q learning instead. It is called deep Q network. Okay, or it can be neural network, normal neural networks, or deep neural network. Okay, depends on complexity of your environment. Okay, also if we have a partial observability, so you don't know in which state you are, you cannot apply q-learning directly. You need to go to the hidden Markov process that we have seen before, or you can go to the partial observable processes. Okay, and what else? Non-stationary environment, also a q-learning, because in the q-learning when you complete the off policy cases, it means that you repeat it like 1,000 times, you learn the total like environment, and now you have the optimum movement in that environment. But what if the environment is changing every time? It changes a lot, not like a simple change, but it changes in hard in aggressive way. So in this case, it is hard for the Q learning to converge. So in this case, we need to use adaptive learning or neural networks as well. So here we have some examples that you can, depending on the example that I explained now on the whiteboard. So you can see, and I put it like in numbers in order that you can understand very well how things are going on the Q learning. Okay, and also I added the Octave code for the, you can see this is the Octave code for the reinforcement learning. So it is very simple, just a few lines. And also another example here. Then I put also another example, and this example is added, is a new example, is not in the previous slides. So in this example, I want to play against someone, okay? And the game is very simple. The game is there. So the AI agent select a number, 1, 2, 3, 4. Select any number randomly. And the opponent, you have opponent, and the opponent also select a number from the same set, 1, 2, 3, 4. And your opponent playing this game, they follow certain strategy. For example, they play 1 with 30%, 2 with 20%, 3 with maybe 10%, 4 with 40%. The total number of percentage should be 1. So your opponent play with certain strategy, and you don't know, your artificial intelligence agent doesn't know the strategy. It is hidden, the strategy of that opponent. So both of them, the AI agent and the opponent, both of them, they don't know the strategy of each one other, and also both of them, they don't know the selected number. They don't know the selected number. The opponent, they know, of course, it is on selected number. Your AI agent knows it is on selected number, but they don't know the selected number of the other party. Okay, there is another now evaluation item. The evaluation, they will add both numbers, that the number that you generated, the number generated by your opponent, they add them together. If the summation is a prime number, you will get reward. So you don't know. For example, you select 1, your opponent select 4, 1 plus 4 is 5. So you will get reward. But the reward could be also that your opponent selected 2, because 1 plus 2 equal to 3. 3 also is a prime number. You don't know, actually. You don't know from where this prime number came. But what you know, that you get reward. and you repeat this game many, many times. What I want my AI, I want to write a code that my AI will understand and know how the opponent playing. And then they can select always the best number in order to beat your agent. So it is interesting and very simple, extremely simple game, but at the same time, it is very interesting. The nice thing here that you have a single state. We don't have movement from different states, but we have different actions, single state and different action. So this is the code to play this game. You can also generate this code by using Julia or Python. You can, of course, take the assistant from ChatGPT, but it is important that you study the code and how it works and how it applies this Q-learning in order to have this intelligent AI that it captured the way of your opponent, how your opponent playing. And you can try this with yourself. You can also play this with yourself, and you can see how AI could capture your way of thinking. It is very interesting way. And finally, the nice thing that with AI agent that we don't have data to learn, that we don't teach any data, but it capture the behavior, it learns by itself. So um, if there is AI based innovation, you will find the reinforcement learning, because it can innovate some way of solutions that without showing it how to do it. As I said, we have many different algorithms for learning of reinforcement learning algorithm, but because this course we have almost all kinds of learning algorithms, so I didn't go through details of every algorithm because we have plenty of them. But the concept is the same. The concept that I explained today is the same, which applied for other algorithms as well. Thank you very much for you today. And last lecture will be, I think it will be in Wednesday. So in Wednesday, it will be very light lecture. There is no quiz for next lecture, but we will talk. It will be interesting because we will see how to merge different algorithms together. Maybe we'll let us talk a little bit about generative AI, and also about ethics of machine learning. What are the ethics of machine learning that we should be aware of? So it will be very interesting, just discussion, general discussion for the next and last lecture. Okay, thank you very much. Now, if you have questions, please you can write down your questions on the chat.